Browsers are a unique constraint in web application development. A few years ago, targeting multiple browsers meant writing completely different code paths for each one: Internet Explorer, Firefox, Chrome, Safari, all with wildly different behavior and performance characteristics. The result was bloated code and degraded performance as you accumulated workarounds. Today, browser vendors collaborate much more closely on standards. If you build on a solid abstraction layer, jQuery is the canonical example. Most of your code will run correctly on every major browser without modification. The remaining 10% of browser-specific fixes are small and manageable. But there's a critical insight: keeping these abstraction layers up to date is performance work, not just maintenance work. Browsers release new versions frequently, and those versions often improve JavaScript engine performance, add better DOM APIs, and fix the exact edge cases that abstraction libraries were working around. A newer version of jQuery, for instance, can take advantage of newer browser APIs that are faster than the old workarounds. This is measurable. A JSperf benchmark comparing jQuery 1.3 through jQuery 2.1 on Chrome shows that jQuery 1.3.2 is 77% slower than jQuery 2.1.0 for the same operations. The oldest version is nearly 5 times slower. If you're running jQuery 1.x from 2010 in a modern browser, you're leaving substantial performance on the table for no reason. The lesson is not to blindly update every dependency, it's to understand that browser-facing abstractions improve performance over time, and staying on old versions has a real measurable cost. Test your updates with JSperf or a similar tool to confirm the improvement before deploying. And always keep your eye on what browser APIs your abstraction layer uses. If the browser ships a native implementation of something that was previously polyfilled, the polyfill becomes deadweight. Performance is not a single knob you turn. It's a mixture of choices and variables that interact with each other across every layer of your system, from the JavaScript engine to the network to the browser. Chapter 7 ends with a framework for thinking about performance decisions systematically. The first variable: choose your platform wisely. The best platform in general might not be the best platform for your use case. Node.js is excellent for I/O bound, concurrent workloads, but if your application is CPU-intensive computation, you should be evaluating whether Node.js is the right choice at all, or whether you need to offload certain operations to worker processes or native modules. The second variable: define your data structure early. Choose your database server based on your data shape and access patterns, not just familiarity. Plan for data growth. What does this look like at 10x the current scale? A design that works at 10,000 users might fail completely at 100,000. The third variable: plan your modules and test everything. Create a development environment that can be replicated so new developers can get productive quickly. Every module should have tests. Testability forces you to think about boundaries and dependencies, which leads to better architectural decisions. The fourth variable: choose a target environment and start there. Don't attempt to develop for every device and every browser simultaneously from day one. Pick your primary target, the device and browser your core users actually use, and build the best possible experience for it. Then expand coverage once the core is solid. The overarching theme: plan before you build. A bad choice made at the beginning is exponentially more expensive to fix after deployment. It's better to spend an hour thinking about your data access pattern before writing code than a week refactoring it after users are hitting production. That planning time is itself a performance investment. It's your own development performance.